Okay, today I'm going to talking about the basic concept which most of you are very familiar with, infinity. I think most of you know this kind of concept, infinity in mathematics form is just like this. But what I want to talk about is, I want to ask you a question. Does all infinity the same? Or some infinities larger than other infinities? This sounds like a weird question, right? Do you have any ideas for these questions? No?
Not really.
Okay, so let me ask you another example, simple example. There is a famous paradox in ancient Greece called the arrow paradox. Suppose we have an arrow, this arrow, and it's in flight. It's moving forward, but at any given time, it is stable. You can find the position of the arrow at any given time, right? So for any time, it is stable. But after some time duration or some time intervals, it's moving forward. That is not sounds weird since it does not change at any given time, but it does change after some time durations. Another expression of this problem is, suppose we have two segments. The line, for example, is between 0 and 1. So this segment has a length, right? The length of this one is just 1 minus 0 is 1. If we have another segment is 2 and 3, between 2 and 3, so the length of this segment is also 1. So the total length of these two segments is 1 plus 1 equals 2. Sounds great, there's no problem here. But actually, if we choose one point of this in this segment, we know that the point does not have length, right? How can we define a length for a single point in a mathematical way? So this segment is consists of infinite number of points, right? But each point does not have length. How can a segment which consists of all these points have length? Think about it. This is the time interval. When the arrow travels from one time to another time, which can be compared to this segment, and in each time point, the arrow is stable, which means that the length of this travel is 0. It does not change. It is stable at any given time. But after some continuous time, it's moving forward to some other place, which means from 0 to 1, for example. When t equals 0, it is here. When t equals 1, the arrow is here. So there are some difference between these two states. So there is a length between these. But how can we explain this? It's a weird result since single point does not have length, but the set of all these points have a length. To explain this, we have to introduce two concepts of the infinity, which is the answer of my first questions. The infinity are not the same. Some infinity is larger than other infinities. We call this uncountable infinity. Uncountable infinity. What does that mean? We know that given a set, we can find the size of this set, right? If for a finite set, it's very easy. For example, if we have 1, 2, 3, the size of the set is just 3, since we have 3 elements in the set. We have another set which maybe is 4, 5, 6. The set is also 3. But if we extend this set to infinity, what will happen? How can we compare two different infinity sets, the size of two different infinity sets? For example, how we compare the size of the all positive integers, n, which is 1, 2, to infinity, or the numbers which are even, which means 2, 4, 6, 8. Does these two infinite sets have the same size? Or it doesn't?
Same set.
Yeah, why?
Because it's infinity.
What? I'm sorry.
So when you think it's like the whole total numbers, and there's not much difference as a size.
Yes. But how can you define the size? how can you compare these things in mathematical way? You can find a one-to-one mapping between these two sets, right? We know one-to-one mapping means you have one map, one set like this. I will reverse this. And another side like this. And there are several elements in here, several elements here. We can find a one-to-one mapping, which means each element we have a unique element corresponding in the element that set. And all the elements we can find a unique corresponding items in another set. That's the one-to-one mapping. And what we do here is we find a one-to-one mapping between these two sets. It's just equal to 1, y equals 2 times x, right? Given any x in this set, we can find a unique y in this set. And inversely, it is the same. Given any kind of y, you can find x, which is also unique. But it is also weird, right? Since this set is just a subset of this set, it's part of this n, right? Yeah, it's part of it. And how can we say that these two sets have the same side? Even one set is part of it. That's why we need this uncountable infinity and countable infinity. For example, if we have, we can define two sets which is not different kind of size. And the proof is very difficult, but I will just with the proof here and state the result. It is that this set, the set consists of all positive integers, and the set consists of all real numbers to the minus infinity to infinity. These two sets are not the same size. This one is much larger than this one. And I omit the proof here. But the reason I say this result is this result can explain the paradox, the error product here. Why? Since when we consider this, the measure of the length is the sum of all points length. This is not true. Why? Since when we consider sum operations, we're actually doing these things. We are counting the sum operations. For example, when we define sum, we define the sum of two numbers. 1 plus 1 equals 2, right? If we want to 1 plus 1 plus 2, we have first calculate this, get 2, then use this 2 to calculate the another sum operations, which means we are counting the sum operations. There are 2 sum operations here, and we are going forward. There are 3 operations, 4 operations, and infinity operations. But all of these operations need to be like this. It has to be arranged in this way, 1, 2, going to infinity. However, we know that this infinity is much larger than this one, which means